Hello friends, welcome to video lecture on fluid mechanics. In the today's lecture, we'll continue with the discussion related with the fluid dynamics. We'll discuss about the application of Bernoulli's equation to Venturimeter. No doubt, here the three applications related with the Bernoulli's theorem with us: Venturimeter, orifice meter, then pitot tube. In the current lecture, we'll continue with the application of Bernoulli's equation to this Venturimeter. So Venturimeter is the device used for measuring the rate of flow of a fluid flowing through a pipe. It consists of three parts. So first one is the thing but the converging part. So here is the converging part, then throat and diverging part. So it is based upon the principle of Bernoulli's equation. The expression for the rate of flow through Venturimeter, just here, consider the Venturimeter fitted in a horizontal pipe through which the fluid is flowing, say water, as shown in this figure. Okay, so let us consider this one. D1 is the diameter at inlet or section number 1. So corresponding pressure is nothing but the P1, and corresponding velocity of the fluid at section number 1 is nothing but the V1. So small a indicate the area at the section 1. So that can be analyzed by using this one, this formula, pi by 4 into d1 square, in this way. So A2, P2, V2, A2 are the corresponding values at the section 2. So here is the section 2. So applying the Bernoulli's equation at section number 1 and section number 2. So this actually can be more clear to you with the help of this diagram. This one, Venturimeter. Here the flow actually coming from that converging portion, then passing through this throat portion, and again that is diverted from this diverging portion. Okay, now as far as concerned with our study, the measurement of this flow is done with the help of this Venturimeter by applying here the Bernoulli's equation at the two section. So here we consider the section number 1, here we consider the section number 2. Okay, now already we have seen D1, P1, V1 are the corresponding values at section 1. Similarly, P2, P2, V2, A2 are the corresponding values at the section number 2. So you will apply the Bernoulli's equation at section number 1 and section number 2. So here we can get that relation P1 divided by rho g plus V1 square by 2g plus Z1 equals to P2 divided by rho g plus V2 square divided by 2g plus Z2. So as pipe is horizontal, in this case datum head, that is Z1 and Z2, both this term becomes the same. Now if you just see here in this equation, the Z1 equals to Z2 means this get cancelled, and whatever the remaining part we are written as it is. Now just separate the pressure term and velocity terms. So P1 minus P2 divided by rho g equals to V2 square divided by twice g minus V1 square divided by twice g. In this way the relation will come. So what's about this P1 minus P2 divided by rho g? This is nothing but the difference of pressure head at the section number 1 and section number 2. Okay, so substituting the value of this P1 minus P2 divided by rho g in above equation, so what we get here? So V2 square divided by twice g minus V1 square divided by twice g. So this is nothing but the H. So H equals to, we can get this term. Now applying the continuity equation at section number 1 and section number 2. So continuity equation with us, A1 V1 equals to A2 V2. So what do we get here? We can get the V1 equals to A2 V2 divided by A1 in this way. Now substituting these values of V1 in equation number 6. Here is that equation. So H equals to V2 square divided by twice g. This term will remain as it is, minus you have to replace this V1 by A2 V2 divided by A1. Now expand this term and just see here, V2 square divided by twice g. This term is taken common, so here only 1 will remain, minus from this also we have taken this V2 divided by twice g is common, so here we can get v2 square, a2 square and a1 square. Okay, whatever the terms remains here are only related with the area. So here a2 square divided by a1 square will remain. So make the base common here. So we can get v2 square divided by twice g into bracket a1 square minus a2 square divided by a1 square. Okay, so from this relation get the value for v2. So v2 square equals to twice gh. This term will come here. Okay, that's why you have to multiply by this 2g to this h term. So 2gh multiply by here a1. Okay, this one a1 square goes in numerator and this comes in denominator. Okay, so here v2 square with us. So to get the v2 you have to take the square root from both the side. So in this way I can get the square root of twice gh into a1 square divided by this one a1 square minus a2 square. So if I take the square root of this one, what we get here, a1 into this term will remain as it is, this term will remain as it is. Okay. Square root of 2gh divided by square root of a1 square minus a2 square. So with the help of this relation you can get the discharge q equals to a2 v2. So a2 you have written as it is, and what's about the v2, this term already with us, just substitute this here, a1 divided by square root of a1 square minus a2 square multiply by square root of 2gh. So here a1 multiply by a2, a1 a2 divided by this term and this term is as it is. So equation number previous one gives the discharge under ideal conditions and is called theoretical discharge, but in the actual case this theoretical discharge means the actual discharge is always less than the theoretical discharge. Okay, for that we just say the CD is nothing but the coefficient of the Venturimeter. It is its value must be less than 1. Okay, so here we can get the actual discharge value is less than the theoretical value. Okay, that's why here the CD is multiplied and the value for this CD is always less than 1. So value of the H is given by differential U-tube manometer. So in case number 1, let the differential manometer contains a liquid which is heavier than the fluid flowing through a pipe. Now focus on this one. Here if we consider the manometer, then whatever the fluid flowing through this pipe we are considered as heavier than whatever the fluid passing through this Venturimeter. Okay, in that case SH indicate the specific gravity of the heavier liquid and SO indicate the specific gravity of the liquid flowing through pipe. So X indicate the difference of the heavier liquid column in U-tube. So here in case of the differential manometer contains a liquid which is heavier. So heavier liquid when we consider, then we can get the value for this one H. So actually H with us. The help of this relation we can get the value. So H equals to X into SH by SO minus 1. In the second case, if I consider the reverse case, let the differential manometer contains a liquid which is lighter than the liquid flowing through the pipe. The value of the H is given by, so here instead of this SH by SO minus 1, the reverse case will come here. So here H equals to X into 1 minus SL divided by SO will come. So this L indicate the lighter liquid. Okay, specific gravity of the lighter liquid in U-tube. So what's about this one? Specific gravity of fluid flowing through pipe. So X indicate the difference of the lighter liquid columns in U-tube. So in the third case, if I consider the inclined Venturimeter with the differential U-tube manometer, then the above two cases are given for the horizontal Venturimeter. This case is related to inclined Venturimeter having differential U-tube manometer. Let the differential manometer contains heavier liquid, then H is given by, in this case whatever the case number 1 we are discussed, that case is the similar one. but here in this case we have considered the inclined venturimeter. Okay, for that H is nothing but the P1 divided by this one rho g plus Z1 minus this one P2 divided by rho g plus Z2. So in this case, as the inclined venturimeter we are considered here, then the value for Z1 and Z2 is the different one. Okay, so this relation we can get here, x into sh divided by s naught minus 1. So same actually relation we are considered here, only difference will occurs towards the left side. Now similar actually case with the venturimeter, in which the differential manometer contains a liquid which is lighter than the liquid flowing through a pipe. The value of the H is given in this way. So here we can just get the difference. Instead of that SH by S naught minus 1, here 1 minus SL divided by S naught will come. So other terms will remain as it is. Now we'll move towards some of the numericals on the same topic. A horizontal venturimeter with the inlet and throat diameters 30 centimeter and 15 centimeter respectively is used to measure the flow of water. The reading of differential manometer connected to the inlet and the throat is 20 centimeter of mercury. Determine the rate of flow. Take CD equals to 0.98. Now our target is to find out the value for the this one flow rate or discharge. Okay, for that this is the formula with the CD into A1 into A2 divided by square root of A1 square minus A2 square into square root of 2GH. Now just say we require this one by one term. Okay, so for that if you just see the diameter at the inlet and at the throat portion is given, from this diameter first of all get the area. So A1 we can get with the help of this one, this formula pi by 4 into d1 square. Substitute the value of d1 here, so get the value for A1. Similar case with the A2. Then the value for the CD already with us 0.98. Reading of differential manometer with us 20 centimeter of mercury. This information already given. So in case of the when here just here the difference of the pressure head is given by, if you just here the mercury is given, the reading of the differential manometer is connected to the inlet and the throat is 20 centimeter of mercury. So this becomes actually a heavier fluid. Okay, so that's why you have to write this relation H equals to x into sh divided by s naught. So we know the specific gravity of the mercury and specific gravity of the water. So here the specific gravity of the mercury with us 13.6 and specific gravity of the water with us 1. So from this relation you can get the value for the H. Substitute the value of x, sh, s naught, then here okay 1 already written. To the calculation we can get the value for H as 252 centimeter of water. The discharge through venturimeter is given by this relation, already this relation with us. So substitute everything in that equation and do the calculations. CD with us A1 A2 and A1 A2 2GH. H already we have calculated from this relation. Okay, substitute everything, do the calculation. We can get the value for Q equals to 125.756 centimeter cube per second. Okay, if you just convert into liter, we can get 125.756 liter per second. Now we'll move towards next problem on the same topic. An oil of specific gravity 0.8 is flowing through a venturimeter having inlet diameter 20 centimeter and throat diameter 10 centimeter. The oil mercury differential manometer shows a reading of 25 centimeter. Calculate the discharge of oil through the horizontal venturimeter. Take CD equals to 0.98. So in this case the specific gravity of the oil with us 0.8 and specific gravity of the mercury with us 13.6. Now see the reading of differential manometer with us x equals to 25 centimeter. Now see the difference of the pressure head. So from this we can get the value for H. So here this one with us 13.6 and here the specific gravity of oil with us 0.8. So substitute here and get the value for the H. So we can get 400 centimeter of oil. Then see the inlet diameter with us 20 centimeter, then throat diameter with us 10 centimeter. Okay, so from this one get the value for A1, A2. The value for the CD already given in the problem. Just substitute the value of CD, A1, A2, G and H, etc. and get the value for the discharge. So here we can get the 70,465 centimeter cube per second, and if you just convert into liter, then we can get the 70.465 liters per second. Now we'll move towards next problem. Find the discharge of water flowing through a pipe 30 centimeter diameter, placed in an inclined position where a venturimeter is inserted. Having a throat diameter 15 centimeter, the difference of the pressure between the main and throat is measured by a liquid of specific gravity 0.6 in an inverted U-tube, which gives a reading of 30 centimeter. The loss of head between the main and throat is 0.2 times the kinetic head of the pipe. So whatever the information given regarding the inlet diameter and diameter corresponding to that throat, from that to get the value for the area. So this one given 30 centimeter, this one given 15 centimeter, substitute here, and here we can get the D2 as, here we can get the A1 as 706.85 centimeter square and A2 as 176.7 centimeter square. A reading of differential manometer with us x equals to 30 centimeter. Then the difference of pressure head H is given by, so here you can get that difference of pressure head P1 divided by rho g plus Z1 minus P2 divided by rho g plus Z2 equals to H. Also this relation with us, H equals to x into 1 minus SL divided by S0. So value for the SL is given. SL means here the specific gravity of the liquid corresponding to that throat portion or the fluid flowing through this with us 0.6, and the fluid through this one S0 1 actually with us in specific gravity of the fluid through this one with us as 1. Okay, so if you just see here, we have to write this formula in this way: H equals to x into 1 minus SL divided by S0. So substitute the value for this SL and S0 and do the calculations. We can get 12 centimeter of water. What's about the loss of head? So HL is nothing but here we can get 0.2 multiplied by kinetic head of the pipe. So 0.2 multiplied by, so kinetic head of the pipe is nothing but V1 square by 2G. Now apply the Bernoulli's equation at section number 1 and section number 2. So here we can just apply that Bernoulli's equation at section number 1 and 2 in this way: P1 divided by rho g plus Z1 plus V1 square divided by 2G equals to P2 divided by rho g plus Z2 plus V2 square divided by 2G plus HL. So in this way we can get the this one rho P1 divided by rho g plus Z1. Okay, this term we have written in this way, and this term we have taken towards the left side. At the same time we have taken this term towards the left side to get the value for this one head loss. Now if you just see here, this term and this term indicate H. Okay, so H 12 centimeter of the water, this information available here, 12 centimeter of water. Okay, so already the value for the H with us. Okay, this one and this one, the difference between the this one and this one, already the H equals to 12 centimeter of the water with us. So what's about this HL? HL is nothing but the 0.2 into V1 square divided by 2G. So towards the right side of this equation, just put this one 0.2 multiplied by V1 square divided by 2G, and towards the left side of this one, so this one with us 12, and what's about this one, V1 square divided by twice G minus V2 square divided by twice G. Just write this term as it is. Okay, so move towards our next step. Take this term towards this side and just say towards right side we can get the 0. Okay, so from this if I apply the continuity equation at section number 1 and section number 2, section number 1 is here, section number 2 is here. If I apply the continuity equation, so here in this case we can get the value for V1. So V1 is nothing but here A1 divided by A2 V2. So A2 with us, A1 with us. So A2 with us, this term, and A1 with us, this one. Now continue this one. Substitute the value for this one A2 A1 in this way, and get this velocity V1 in terms of the V2. In this way V1 equals to V2 divided by 4 will come here. Now substituting this value of V1 in equation number 1. So equation number 1 with us here, 12 plus 0.8 into V1 square divided by 2G minus V2 square divided by 2G. So in this case just substitute the value for V2 V1. Okay, so we can replace this that V1 by V2. So V1 in terms of the V2 with us here, in this way we have to replace that V1 term by V2 by 4 in this way. Now if you look towards this equation, only V2 is unknown here. Solve this equation for V2 and get the value for V2 as 157.4 centimeter per second. Now what's about the discharge? We know the discharge Q is nothing but the A2 V2. What's about the area? Area A2 with us 176.7 multiplied by V2 with us 157.4. Substitute here, do the calculation, we can get 27,800 centimeter cube per second. After this, convert into liters by multiplying 10 raised to here -3. If I multiply to this term, we can get in terms of liter as 27.8 liters per second. Thank you. I hope whatever the theory as well as problems discussed in the today's lecture clear to you.